In this lecture video, we estimate the beta parameters in the multiple linear regression model of example 3.1 in the text. Here's an overview of what we'll be looking at in this video.
All right, welcome back. In this lecture video, we're going to take a detailed look at example 3.1 in the text, which is on the delivery time data. And so let's remind ourselves what this is all about. So a soft drink bottler is analyzing the vending machine service routes in his distribution system. He's interested in predicting the amount of time required by the route driver to service the vending machines in an outlet. This service activity includes stocking the machine with beverage products and minor maintenance and housekeeping. The industrial engineer responsible for the study has suggested that the two most important variables affecting delivery time, which is our response variable Y, are the number of cases of products stocked, X1, and the distance walked by the route driver, X2. The engineer has collected 25 observations on delivery time, which are shown in table 3.2 of the text. And again, this is an expansion of the data set that was used in example 2.9. Now, in this example, we're going to fit the multiple linear regression model given here, y equal to beta 0 plus beta 1 times x1 plus beta 2 times x2 plus the error term epsilon. We're going to fit a multiple linear regression model to the data in table 3.2. Now, here is the data shown in table 3.2 that is provided in the slides here. And again, the model that we're going to be fitting is given here. All right, and so remember that Y is the delivery time in minutes. That's the response variable. X1 is the number of cases. X2 is the distance in feet. Now, when we went through this in the previous lecture video, we looked at these slides briefly. We're going to be showing how we can generate this kind of output on our own. And so here was a slide that they're using to give a visual representation of the relationship between the response variable delivery time and each of the two explanatory variables, number of cases and distance walked. And it also shows a graphical representation of the relationship between x1 and x2. So let's take a look and see how we can generate this on our own. And what we're going to be using in this example is going to be two statistical packages. These are two of the statistical packages that are used by the authors of the textbook. In particular, we're going to be using SAS, and we're also going to be using MINITAB, all right, so to give you a couple demonstrations of how we can do these things. And so let me switch over to back over to my SAS program, my SAS window. And so here again is the description of the example. Let me scroll down a bit, and you'll see here that I am creating a temporary SAS data set called delivery time. And I'm bringing into the data set the observations that are given in the data set. So if I scroll back over here to the slides, all right, if you take a look at the data that we've got here, 16.68 for delivery time for the first observation, 7 cases and 560 feet walked. All right, and so that's the data that we've got right here. And so to create a temporary SAS data set, I use the data statement. All right, this is called a data step. And I give the data set a temporary or a name. This is because I don't have a libref here in front. This is just going to be a temporary data set in the work directory, in the work folder for SAS. And we can give this any name that we want, but I'm going to give it something descriptive, and I'm going to call it delivery time. Then we're going to tell SAS here that we're going to be inputting 3 variables, in this case, y, x1, and x2. And by default, the variables listed here are going to be numeric. If we wanted to enter character data, we would have to precede it with a $sign. And then we tell SAS that the information in subsequent lines would be the data. And one way to do this is to use the statement cards, all right? And that harkens back to when programs and data were read into a computer on punched cards. We could also use the statement, let me see here, data lines, like that, all right? And that would do the same thing, but that's more typing, isn't it? So I tend to just use the card statement. All right, and then we have the data incorporated as it's shown here. And notice that I've got each observation on a row. The data are not separated by commas in this case. They could be, but then I'd have a little bit of more overhead up here to tell SAS what the delimiter is. But what I do have here is a tab. Instead of a space, I've used a tab so that these line up so that you can see these easier as you watch this video. But we could use spaces instead. But if we were to do that, then they wouldn't necessarily be lined up very well. So let me just show you what that would look like. And it's a little bit more difficult to see it. All right, but let me go ahead and I'll reinsert these tabs. And that gets them lined up very nicely. Okay, so we have our data, and then at the very end of that, we have a semicolon. And then what I'll do is I'll have a run statement, all right, to tell SAS that go ahead and create that temporary data set. And then once we do that, we can do some further processing. And so let me just show you what we're going to do here. The first thing I would do after I create the temporary data set is to print a listing of the data set, just so that I can make sure that the data the data set was created correctly. And just it's a quality control check. Then the next thing I want to do is I'm going to show you a couple different ways of creating statistical graphics like this. And we'll take a look at that. So let's go ahead and let me create the data set. And what I'm going to do is create the data set, and then I'm going to print a listing of the data set just so that we can check to make sure that there were no problems, that it was created correctly, and then we'll proceed from there. And I'm just going to run that subset of the program by highlighting the statements that I want to run. And then I'm going to click the run symbol up here, the submit symbol, the little running man. I know that's kind of hard to see. And so let's do that. And so then here I have SAS is taking me over to the results window. And we can see here that we've got 25 observations as we are supposed to. Let's go back and take a look at the slide. We can see here that we have 25 observations, and we can visually check to make sure that we have the data have been incorporated correctly. Okay, so we have created that temporary SAS data set. And now what I want to do is first, let's use the SGPLOT procedure to create a scatter plot of Y versus X1 and Y versus X2 separately, right? So I'm going to create two separate scatter plots. And so let's first create a scatter plot of Y versus X1. And let's see here, I guess I need to fix my titling, don't I? I'm using SGPLOT. Let me create, fix that. And I'll do that there. So with these first two plots, I'm going to be creating these with PROC SGPLOT, and then I'll use SGSCATTER down below. But let's take a look at this. So let me create this first scatter plot. So again, I'm just going to highlight the code that I want to run, and then I will come up and press the submit button. And you can see here that we get a really nice little scatter plot, a basic scatter plot of Y, the delivery time, versus X1, which is the number of cases delivered. And we can see here that we have an increasing trend, and it certainly looks like that's a linear trend. If we were to fit a straight line over these data, that would fit fairly nicely. All right, and if we go back over to our slide here, that plot that we just created is this portion of this scatter plot matrix. And so you can take a look at that and then compare it to what we got here, and you can see that we get the same plot. Okay, now let's create a scatter plot of Y versus X2. So the delivery time versus the distance walked. And so I will highlight that code, and then I'll press the submit button, and we get the next scatter plot. And again, it's very easy to get this. All right, and you see that this is the same plot that shows up in this portion of the scatter plot matrix. By the way, in the name of this particular procedure, SG, that stands for statistical graphics. All right, and so this is a really nice way to get some statistical graphics out of SAS. You don't have to, you can see here there's not much code that's required. What I'm doing is I'm invoking PROC SGPLOT. I tell it the data set that I want to use. All right, and then within the PROC, I'm going to issue the scatter statement. This tells SGPLOT, obviously, to create a scatter plot of using the two variables that are listed after that. So the Y variable is Y, obviously, and the X variable, which goes on the horizontal axis, in this case is X1, okay? And then in this plot down here, the horizontal axis would be X2. And again, that creates, let me see here, that creates these two scatter plots. But what if we want something like this? If we want a scatter plot matrix, right, that has all of these plots together, and in addition, not only do we get scatter plots of the response variable versus each of the two explanatory variables, but we get a scatter plot of the two explanatory variables together as well. Well, we can use the SGSCATTER procedure to do that. And the syntax is very, very similar, at least on the invocation of the procedure. Instead of SGPLOT, it's PROC SGSCATTER, statistical graphics scatter. We tell it the data set that we want to use. And then instead of the scatter statement, it has what's called a matrix statement. And this is just telling SGSCATTER to create a scatterplot matrix using the variables listed after that. All right, and so you can see here that we want to create a scatterplot matrix using the response variable y, and then the two explanatory variables x1 and x2. And so let me go ahead and run this, and let's see what happens. And so you can see here that we get a very nice graphic. It's a scatterplot matrix. And with this particular invocation, without really specifying any options, we get something that is very similar to what we showed here. And if we had labeled or named our variables time, cases, and dist, then we would have had that same information down the diagonal. All right, but we labeled our variables y, x1, and x2, all right, to be consistent with the notation that's used in the example. And so with this scatterplot matrix, you can see that, again, we have pairwise scatterplots among all three of the all pairs of variables. And so this would be a scatterplot matrix of y on the vertical axis and x1 on the horizontal axis. And again, that is the same as this scatterplot. And then in the upper right corner of the scatterplot matrix, we have a scatterplot of y on the vertical axis and then x2 on the horizontal axis. And so that is the same scatterplot as this scatterplot right here. All right. Now, this is a symmetric matrix. And so, but there's one little difference in that symmetry. This plot here in the position row 2, column 1 is equivalent to this plot in position 1, row 1, column 2, with the difference that it's flipped about the equiangular line, right? It's flipped about the y equal x line. And so in this plot, the horizontal axis or the vertical axis would be x1, all right, and the horizontal axis would be y. And so you can see here that if you flip this plot about that equiangular line, then you get this plot. And the same thing with this plot down here, the same type of thing. All right, this is equivalent to, or this is the mirror reflection of this plot, again, about that equiangular line. Now, one thing, one nice thing that we get out of this scatterplot matrix like this is that we get the scatterplots of the explanatory variables. And so we're able to see how strong, assess the nature of any kind of a relationship between two variables and get a sense of how strong that relationship is. And so we can see here in the plot in row 2, column 3, that, so this is a plot of x1 on the vertical axis versus x2 on the horizontal axis. And you can see here that there is an increasing trend in general. And it does look like that would, that a straight line would fit that relationship pretty well. And so, that might be something we want to keep in mind as we continue analyzing and this data and performing a regression analysis. We'll talk about why a little bit later. But we can see here that scatterplot matrix gives us a lot of information in a very small amount of space, graphical information that allows us to assess the type, the nature, and the strength of the relationships between the different variables that are included in the model. Now, all of these plots contained in this scatterplot matrix are bivariate graphical summaries. They're scatterplots of pairs of variables. There's really no univariate summary provided here, but we can get that kind of information by adding a very convenient and simple option to PROC scatterplot in the matrix statement. And so that's what we're going to do down here. And you can see here that in the matrix statement as an option, and by the way, options are listed after a /, we're telling the matrix statement to, instead of including the variable names on the diagonal of the scatterplot matrix, we want histograms of the individual variables. So the option would be diagonal equal to, and then a histogram in parentheses. And so if we go ahead and run this, then we will get a scatterplot matrix like the one above, but it's got these nice histograms for the individual variables down the diagonal. And one thing that allows us to do is to get a sense of the shape of the distribution of the variables, which, in some cases may be useful. It may be useful to know how the explanatory variables are distributed. So that's, this is, again, a nice graph. It's got both univariate summaries of the variables and bivariate graphical summaries in the sense or provided by the pairwise scatter plots. Okay, now I want to continue on, and now we're going to get into estimating the parameters, and in particular the beta parameters for the multiple linear regression model. And so you'll recall that in order to do this, a convenient way to do this is to express the system of equations that are defined by the regression equations, or the regression equations for each observation in matrix format. All right, and so to do this, in fact, let me just go up here real quick. And so you can see here that for each observation, and again, this is in the notes that in your textbook, and also we covered it in the previous lecture video, but for each observation, I going from 1 to n, we have the regression model for that observation. And we can express that collection of n regression models using a single matrix equation as given on this slide. So a bold y, that's a vector of responses, equal to x times beta plus epsilon, x being the design matrix, that is an n by k plus 1 matrix. Bold beta is a k plus 1 by 1 vector of parameters, and these are unknown, they've got to be estimated. And then the epsilon, bold epsilon, that is an n by 1 vector of residuals that is unobserved, and at some point we would want to estimate those error terms. But this is the model for the collection of regression equations expressed as a single matrix equation. Now, with that representation, and I'll skip over the details here, but we'll go right to this slide, which shows us the formula, again, is expressed using matrix notation, of the least squares solution, or the least squares estimator of beta, right? So beta hat being equal to the inverse of x prime x times x prime y. And so let's take a look at that in the context of this example. And so what we've got here, again, this is the original data, and I'm going to express that using, or in matrix notation. And so this would be the vector of responses for the 25 observations. This would be the X matrix, the design matrix, okay? And then we would, using the formulation given in the notes, given in the textbook, we would calculate X prime X, right? We would get this matrix here. We would also calculate X prime Y, which gives us this 3 by 1 vector. We would need to invert the X prime X matrix, okay? And then we would come up with the least squares estimator using this formula here, X prime X inverse at times X prime Y. And that would result then in the least squares estimator of the beta vector, giving these the individual estimators here. So the beta hat would be beta 0 hat would be 2.341231115. This would be the 1.6159 would be beta 1 hat, and then beta 2 hat would be 0.01438 and some change. All right, and so then expressed as writing out the fitted model, this is what it would look like. But let's go ahead and so what we're going to do, we're going to use SAS. Like I said, we're going to use SAS. We're going to use MINITAB, and in using SAS, we're going to use two approaches. We're going to use two procedures, two PROCs, to do this analysis, to do this example where we are coming up with the parameter estimates for the model. And so let me see here. The first thing we're going to do is we're going to use an approach that demonstrates this matrix representation of the data and the matrix calculation of the least squares estimator of beta. All right, and so I'm going to be using PROC IML to do this. IML is the interactive matrix language in SAS. And so what we do is we invoke PROC IML, and then I'll skip the reset fuzz right now. That just tells SAS how to display values that are close to 0. The first thing we want to do is we've got to enter the data in matrix notation. Right, so we've got to enter the data as it's displayed here in the observation vector, and we also have to enter the matrix, the design matrix. All right, and so let's go ahead and look at this. And so here in this first statement, I am entering the response vector y as a matrix literal. In other words, I'm just entering the data values into the vector itself, and so to do this, I give it a name, and I'm going to call it y, and then the assignment operator, the equal sign, and then to define a matrix literal, I'm going to use the curly brackets. All right, so I open the curly bracket that starts the matrix literal, and then I'm going to enter the values, and different rows, or rows are separated by a comma. So every time I have a comma here, right, that's going to tell SAS that what comes next is on a subsequent row. Well, we've only got one value per row, and so for after each of these values, I'm going to have a comma, and so then I enter those values, and then once I get to the last value, I don't enter a comma after that. I enter a closed bracket. All right, and you could put this on the same line like that. Okay, you could put this like that. You could have these on the same row. It doesn't matter, right? For readability, I chose to put these like this so you can see the separate data values. Okay, but you can organize things however you want. Just make sure that observations on different rows are separated by commas. Okay, next we enter the design matrix X as a matrix literal. And we need to be sure that we include a column of ones in the first column because the model that we're fitting has an intercept, right? And so notice that we have a column of ones here on the notes. And so we need to do the same. And so we use the same approach. Data values in different rows are separated by commas. But in the design matrix here, we've got 3 columns in that matrix. And so each row contains 3 values. In the first row, we've got a 1, a 7, and a 560. And so we see that we've got those values here. And then we have a comma, all right? That tells SAS the next data values go in the second row, and so forth. And so this is how we enter the X matrix, the design matrix. Okay, and then we, after the last row, again, we don't put a comma, we just have the closing bracket. All right. Next, what we're going to do is we're going to, again, I like to print out these vectors and matrices as I create them, just to make sure that I've done them correctly. And so in the context of PROC IML, we use the print statement for that purpose. And so what we do is, and there are a couple different ways to do this, but if I tell it to print Y and then X without anything in between here, just white space, then it's going to put those, line them up side by side. All right, now the next thing I'm going to do, and by the way, I'm not going to run this procedure until I've run through everything, because you've got to issue the quit statement in order to do this. So we'll look at everything we're going to do. Okay, so we've entered the data into the observation vector and the design matrix. Then we're going to go about estimating the model parameters. All right, and the first thing we're going to do is calculate the X prime X matrix. And so again, what I'm going to do is I'm going to calculate this guy right here. And now I'm going to keep these, I'm going to do these calculations separately, all right, to coincide with how it's being shown here on the slides and in the textbook. All right, so that you can see that. But in, you know, if we were doing this, you know, for a real analysis, perhaps we may not do these separately. We may put it all into one big expression, but this is for teaching purposes. And so I'm going to calculate the X prime X matrix, which I'll call or label XPX. To do this, there are a couple ways to transpose a matrix in SAS. I like to use the transpose function, which is T. It's just a little bit more visible and easier to see what's going on. And so I will calculate the X prime X matrix, and then I will print that off so that I can check it and we can compare it against what's on the slide. Once we've done that, we're going to calculate the inverse of that matrix. I'll call that inverse XPX underscore INV. And to do that, we're going to call the inversion function. And you know, since I've given that X prime X a name, all right, let's just go ahead and use that, use the resultant matrix that was constructed so that we can save some CPU cycles. All right, and so once I do that, then I will print out that inverse. Let's see, then I also want to calculate, well, let me see here. I'm not sure that I want to go there yet. And so we will just, we'll talk about the hat matrix a little later, but let me see here. Okay, so then once we have, well, you know, one other thing we could do, I haven't done this yet. Let me do this because we want to be able to compare this with the slide. Let me go ahead and we're going to calculate transpose of X times Y. And so we'll call that XPY. And here is what that looks like. Okay. And so we'll do that. And then we will, from that, calculate the parameter estimates. Now, I could go ahead, I could use these, I could multiply XPX underscore inverse times XPY, or I could just, you know, do everything in one fell swoop like I've got here. I think I'll just keep it like that. And then we'll print out that parameter estimator matrix. Okay, so let's go ahead and run this and let's see what happens. And so I'm just going to run everything in here. And so I don't need to highlight anything. I'll just press the running man key, running man symbol. All right, and so let's take a look at the output. And so we can see here that this is, for example, 3.1, the delivery time data, and I'm fitting the model using PROC IML. I first have a listing of the data. And again, note that the Y vector and the X matrix are printed out side by side. And so we could, you know, compare this visually to the matrices we had on this slide in the textbook and in the slides. All right, then we have the X prime X matrix. All right, so you can see the values there. And if we go back and compare that to what's in the slide, we see that we get the exact same values. All right. And then we have the inverse of X prime X, okay, given here. And we could go back and compare that to let me see here. I guess we didn't print that out. Yeah, right there. We've got that right there. And so we could compare that to what SAS gets. Now notice that SAS is not displaying quite as many decimal points as the slide is, but that's okay. SAS is rounding. It's utilizing the full precision of the variables that it has. It's using double point precision. I'm sorry, it's using a double precision, okay, which is very, very precise, very accurate. Okay, and then we have the X prime Y matrix, the X prime Y vector. So 559.6, 7375.44, and 337,071.69. And that is what we had here on this page here. And so once we have that, then we can compute the parameter estimates. And we see that we get that down here. So beta hat has entries 2.3412, 1.6159, and 0.0144 approximately. And that's exactly what we got here in the notes. All right, so that is a demonstration of those matrix formulas to get the parameter estimates using PROC IML. Now, the next procedure in SAS that I want to show you is PROC Reg. Okay, and so Reg obviously stands for regression. And all right, so we have again a data step. Okay, PROC Reg operates on data sets, and so I'm going to use the same kind of data step that I had when we created those statistical graphics. I'll just go ahead and recreate that data set containing the data. And then I've got those plots here. I'll just go ahead and replot those again, that's fine. But the thing we want to focus on is the regression procedure, which is down here. All right, and so we invoke the procedure, PROC Reg. Okay, and then we tell it the data set that we want to use. All right, so we're going to use the delivery time data set. We specify the model that we want to fit. All right, we have the response variable on the left-hand side of the equal sign, and then we list all of the explanatory variables that we want to use in the model on the right-hand side of the equal sign. And that's really all you need to do in PROC Reg to fit this simple of a model and, you know, to do the things that we want to do at this point. Now, I do have a few other options. I have one option here and one additional statement that I'm using. And what I'm wanting to do here is I want to focus on the model, you know, the parameter estimates. That's really all I want to focus on here. And so I'm kind of going out of my way to suppress other default output that PROC Reg generates. By default, PROC Reg is going to generate a fair amount of output in tables and things like that, and also graphics, all right? But that's going to be a little bit overwhelming to look at right now. And so what I want to do, I want to suppress the graphics, and I can do that by saying plots equals none as an option to the PROC Reg, or as a, yeah, these are all options to the PROC Reg statement, even though there's no / there. And then I'm going to issue the ODS select statement with parameter estimates as the argument. And what this is going to do is it's only going to display the parameter estimates table in the output of PROC Reg. All right, and so let's run this and see what we get. Okay, so we get the, you know, we ran those plots that we saw before, but this is the output from PROC Reg down here. And you can see here that we have in the first column, the variables in the model, or the parameters. And so this would be the intercept, so beta 0 hat. And then we have x1, all right? And so this would be, this row corresponds to beta 1 hat, that's the coefficient, that's the beta on x1, and the coefficient on x2 is beta 2. And so this row would correspond to beta 2 hat. And then what we want to focus on here would be the parameter estimates column. And so you can see here that beta 0 hat from PROC reg is estimated to be 2.34123. Beta 1 hat is estimated to be 1.61591. And beta 2 hat is estimated to be 0.01438. And those are the same values rounded to, 5 decimal places that they got in the notes. And it's also what we got using PROC IML. Okay, so those are the two procedures that I wanted to show you in SAS on fitting a multiple regression model. And again, you can see that with PROC IML, we can actually implement these matrix equations that the theory generates for us. The least squares criterion gives us that beta hat is going to be the inverse of x prime x times x prime times y. All right, and so we can see here, it's a really nice way to demonstrate that. But when it comes down to brass tacks and we want to do analyses, it's very easy, all right, to do this without much work by just using PROC reg. And if I wasn't going to be suppressing the output, it would look even simpler because then this is all we would really need. In fact, we wouldn't even need plots equal none. We wouldn't want that. We'd take that out. And so we would be running those statements right there. All right, but I'll keep that in there for now. Now, the other statistical program that I want to demonstrate to you right now is MINITAB. And so let me bring up that window. And so this is what the MINITAB app looks like. And MINITAB has a browser version. It also has a desktop version that runs under Microsoft Windows. And so I'm running this under, this is the actual desktop app that I'm running under Windows 10. And what I've done here is I've taken the data from the spreadsheet, just copied that spreadsheet data into the MINITAB, into a MINITAB workshop. And you can see this is called Workshop 1. I could rename that if I wanted to, but I'll just keep it there. And so once we have copied and pasted that data into the MINITAB worksheet, it's very simple to do a regression analysis. All we need to do is to go up here to the menu, and I'll select the stat menu option. And then you can see all of the different procedures that we can, kind of statistical procedures that are available in MINITAB. We can do basic statistics, and you can see all of the different kinds of things that are available under the basic statistics submenu. We can do regression. We can do a fitted line plot, regression, nonlinear regression. We can do a stability study, orthogonal regression, partial least squares, and so forth. Poisson regression, all right, which is a later chapter in the textbook and in the course. We can do analysis of variance, one-way analysis of variance. We can do all sorts of things here. So, we're not going to spend time looking at all these things right now, but I just wanted to point this out. And, if you're interested, you can get access to MINITAB fairly inexpensively through MINITAB. I will try to find out how much that costs. I think you can get it by semester, and it's fairly inexpensive. So I'll try to get that information to you just in case you're interested. But what we want to do right now in this example is, again, we want to fit a regression model. And so we're going to select regression and then fit a regression model. And you can see here it gives us this description. So we're model of the relationship between categorical or continuous predictors and one response. And that's exactly what we want. Okay, so it brings up a wizard, a dialog box that allows us to enter the variables into the, or to identify the types of variables that we're going to be using in the model. And I've already gone through this, and so these are already populated. let me just take these out, okay, and show you how you would enter these. If you were doing this for the first time, then what you would do is you would first click here in the response box. And then while that box is active, click on the response variable, which in this case is delivery time. That's in column 1, C1 of the data set of the worksheet. And then press the select button, and that puts that variable as a response. Then we could either click each of number of cases and distance and press the select button individually to put them in individually one at a time, or we could just use the shift key and select both. And let me make sure that continuous predictors is the box I'm in, and then go back and select those. And we can see that it puts both of those variables in as continuous predictors in the model. Okay, once we do that, then there are several buttons down here that we may need to take a look at to specify the model and to select the options that we want to utilize in the analysis. And so let's look at the model. And so by default, MINITAB is going to include the included explanatory or predictive variables, the main effects only. It's not going to include interactions or higher order polynomial terms by default. We could add those, but in this example, we only have number of cases and distance included in the model in terms of their main effects. And so we don't need to change anything on this dialog box. Okay, then under options, we're not going to do any kind of transformations on the data. We really don't need to change anything here. All right, the defaults are fine, and so I'll click OK there. We don't need to do any coding. We're not going to do stepwise now. We're not going to do any validation on this yet. But let's take a look here at the graphs button. And for now, let's just let's not have any plots. Let's just focus on the model fitting. And so we won't select anything here. And then the results, let's keep it simple. Now, by default, many of these are going to be selected, but all I really want to look at right now is the regression equation so that we can compare the estimates that we get with those that we got using SAS and what's in the notes. So that's the only output that I'm going to have presented. And so once we have that, we can just click the OK button. Okay, and then you can see here that it gives us the results and actually shows the regression equation. So delivery time being equal to 2.34, that's beta 0 hat, plus beta 1 hat, 1.616 times x1, the number of cases, plus beta 2 hat, 0.01438 times distance. Okay, and you can see here that if we go back over and look at the output from the notes and from the textbook, you see that we get the same answer. It's just rounded to different number of decimal places.
So that's it for this lecture video. I'll see you in the next video.